Get my notes up here again. Well, welcome back, everybody. It's my great pleasure to introduce Ilya Sutskever, who is one of the true luminaries of deep learning. He was there at the very beginning of the current revolution, getting his PhD with Geoff Hinton at Toronto, where he was one of the co-authors on the very seminal paper on AlexNet, which is really the network that by winning the ImageNet competition in 2012 kind of demonstrated to everybody what deep learning was really capable of. Since then, he has done his own deep learning startup that got acquired by Google, and then worked at Google Brain, where he did the sequence-to-sequence model and contributed to TensorFlow. He is a founder at OpenAI, where he is now, and he's going to tell you about some of the recent results there, in particular how they've been able to get AI to play games as well or better than humans. I've been asked to remind you that this talk is being shared on NVIDIA's YouTube channel, and it's being shared publicly. And so please, in the Q&A session, don't say anything NVIDIA confidential. So thanks. Let me turn it over to Ilya.
Thank you very much for the introduction. Yeah. All right. So let's start. At OpenAI, our goal is to build safe AGI and to make sure that it's beneficial and that its benefits are widely distributed. When you think about AGI, we've identified some components that it should have. For example, it would be good if we could achieve difficult goals in simulation. It would be good if we could take those skills that we learned in simulation and take them outside. It would be good if we could learn great world models. And it would be excellent essential to be precise, if we address the issues around safety and deployment. So, in the technical part of my presentation, I'll tell you about 3 of our recent results that I am quite excited about. OpenAI 5, our daughter bot that can play as strong as some of the best humans in this game. Dactyl, our robot which has achieved a very strong level of dexterity, and our results on unsupervised language understanding. OpenAI 5, this is our Dota bot. So the game of Dota, here's a video from it. It's a really complicated game. It is very messy. It combines short-term tactics and long-term strategy. It has the largest professional scene of any esports game, and it has an annual prize pool greater than $40 million. So the game is popular. You can't really see it well on the projector, but this is a photograph from this year's TI, which is the international. This is where we had our bots play against a top pro team, 2 top pro teams. And you can't see it well at the projector, but this is a giant hall, and there are at the giant stage, and there are 20,000 people in it. So I want to elaborate a little bit more about why this game is hard. So I mentioned you got tactics, because there are lots of short-term things going on. And there is strategy, simply because the game is long. It's a long game. It's an hour. A single match lasts an hour. You have partial observability. You don't see the full map. You only see part of it. You have a very large number of heroes with complicated interactions in them. You have 20,000 actions per game, and you have a massive action space. It's almost like it's essentially a continuous action space, because you can select a unit out of a pretty large number of units and tell it where to go. And one other important thing is that the professional players, they dedicate their lives to this game. They put in tens of thousands of hours of deliberate practice of being as good at the game as possible. So it's not an easy game to play. And the other thing that's very interesting and important about this game is that unlike previous games which were used for AI, Dota is closer to the real world. Of course, it's also not the real world, but it is closer. So, how did we do it? We used large-scale RL. That's it. We used an LSTM policy, which is large, a large LSTM policy. I mean, calling it large, I guess is a little bit of a subjective, whether you call it large or not. It's definitely large for an RL policy. Right now, we have an LSTM with 4,000 neurons, so it has about 100-something million parameters. And in terms of its number of flops, it's like the honeybee brain. So we used self-play, and we also used reward shaping. A little bit of reward shaping was important. So what's the key scientific discovery that we made during this work? Is that reinforcement learning actually works. So we already knew that that supervised learning actually worked. With supervised learning, we can pretty much solve any problem we want. If you have a large training set of input-output examples, doesn't matter if it's vision, text, whatever domain, on the input side, the output side, supervised learning can solve it. And if your model doesn't work well, you just need to make it larger and get a little bit more data, and then it will work. And that's the miracle of supervised learning. And we've shown that the same thing holds for RL. We've shown that in RL, if you have a hard problem, it can be a really hard problem, you can achieve super high performance, superhuman performance, if you just appropriately scale it up. Long horizon, that was a big deal. Turns out not so much. And I want to point out that nearly all reinforcement learning experts in the world had a pretty pessimistic view towards RL. They were certain that reinforcement learning cannot deal with long horizons, which justified a lot of work in hierarchical reinforcement learning. And it was just believed that reinforcement learning can't do things. Pure reinforcement learning has only been applied to very simple environments like simple games and little simple humanoid, little simulated robots. So those are toy problems. And you can say, okay, well maybe reinforcement learning can solve only toy problems. And then there's been additional skepticism about reinforcement learning. There's this paper by Henderson et al., which I liked. It showed some issues with reinforcement learning. For example, here you see two curves, which are the random average over 5 runs. But it's the same algorithm in the same hyperparameter, just different random seeds. So, okay, from this you can conclude, clearly this stuff's hopeless. You can forget about it. But our results show that it is not the case. If you scale things up, then suddenly you can solve very hard problems. This is not to say that additional innovation in reinforcement learning is not important. For example, it would be desirable to be able to achieve these difficult goals using much less experience that we use. However, the scientific conclusion from our work is this. If there is a problem which is sufficiently valuable to solve, and it's a reinforcement learning problem, it can be solved. So I want to talk a little bit about reinforcement learning, just explain it to you, because just like the rest of machine learning, reinforcement learning is also very simple. Here is the core idea of reinforcement learning. It's just this slide. Do something and add a little bit of noise to your actions. If you did better than you expected, then make sure that you do those same actions more often in the future. That's it. This is the core idea of reinforcement learning. It's such a simple idea. It's kind of crazy that it works. I'm still amazed. Now, I want to discuss the core improvement on this idea that made it possible to solve something as hard as the Dota game. And this is the idea of the actor critic. With something like the game of Dota, you have 20,000 actions per game. So that means you're going to add noise to 20,000 actions and then see if that did a little bit better than normal, than what you expect or not. That's going to work too, but can we do a little bit better than that? And the key idea of the actor critic method is that you will learn a function that tells you how good the state is, the value function. It tells you how good things are. And the idea of the actor critic method is you add a little bit of noise to your actions, and then you check, and then instead of running the game all the way to the end, you consult your value function to see if things have improved or not. So you're able to reduce the noise, and it turned out to be very important, and it works. So this bootstrapping, that your value function, you say instead of running the game to the end, I'm just going to add a little bit of noise and see, and then look at the value function and see if things improved or not. So it's a bit technical. It's not really important for understanding for the rest of the talk, but I thought you'd find it interesting. Next, the policy. It's just an LSTM. Just an LSTM. We first had 1,000 neurons, then we increased it to 4,000 neurons right now. But the LSTM which played against in TI had only 1,000 neurons. It's pretty cool. Wait, I am 75% sure it had 1,000 neurons. There's a small chance it had 2,000 neurons. Now we have 4,000 neurons. And I want to show you the diagram which shows the architecture. And basically, you got all this complexity, and then it's all fed into the LSTM. So that's the LSTM. And then it's extracted out. The reason we do this is simply because your input, your observations are 20,000 dimensional. And you need to like cleverly use embedding to kind of to feed them in a way that you can, that the LSTM can consume. And this, you know, figuring this stuff out is important, but fundamentally this is, you just want to do something sensible so you can consume your observations and you can produce actions with the right format. I also want to talk a little bit about self-play, which is interesting. Most of the games are against the current version of the bot, and then 20%, I think 20% of the games are against previous versions of the bot. Now I want to share some more cool facts. So the biggest experiments use more than 100,000 CPU cores, more than 1,000 GPU cores, Voltas. The time horizon of RL has been 0.9997, and I think we've doubled it since then. So we're talking about 10 minutes of time, of half-life of time horizon. So it's a pretty good horizon. I want to share some other cool facts about what it's like to work with reinforcement learning. The thing about reinforcement learning is that you just can't tell if you have bugs or not. It's impossible. Because you look at your performance, and your performance can keep on increasing. And you may even have a system which achieves state-of-the-art, or maybe that even like does really well, much better than you expected. And you can still have bugs in your code. And you just need to keep reading the same lines of code again and again and again. And as you fix the bugs, your performance goes up. Another cool thing that we've discovered with our, once we run larger RL experiments, is that this issue has completely gone away. When we run our experiment many times, the curves track each other almost perfectly. All this bad behavior has disappeared. So the high-level conclusion from all this is that if you do things right, you fix all the bugs, and you scale up reinforcement learning, you can solve very hard problems. Kind of like is already the case with supervised learning. So that is a pretty good state of affairs. One other interesting thing that we've done was the introduction of the team spirit parameter. See, in the game you have 5 players versus 5 players. So in order to accelerate learning, we made it so that each player on our team would be selfish and only maximize its own reward. And later on, as the game progressed, we increased the team spirit parameter so that everyone received the rewards of everyone else. And you can see how if you are given shorter-term rewards which are dedicated to you, then you learn faster. And doing that indeed accelerates our learning quite a bit. I also want to show a little bit, to talk a little bit about the rate of our progress. So this is a graph. On the x-axis, you see this spans maybe from May to August. So that's 4 months. That's a 4 months time period. And the y-axis is the estimated MMR. And MMR is kind of like an ELO rating, but not exactly. And so in May, we beat the best team of players that happened to work at OpenAI. And then in June, we beat a team of casters. Then gradually, we reduced the restrictions. Yeah, so here it was still the mirror match. Here we introduced more heroes. Here we added drafting. And here, oh yeah, here's another fun fact. So the game has it's a complicated game and it has many rules. In order to make our work easier, we've added restrictions to the game so that we'll be able to make easier progress before we fix all the bugs. And we gradually were removing all the restrictions. One of the big restrictions that we had right up until the match was the single courier versus multiple couriers. So there is this thing in the game called the courier. And what it does is that it brings items to your heroes. In our before the last public match, we've had 5 couriers, 5 invulnerable couriers which sent items to our heroes. And as a result, it allowed the bot to use a more aggressive strategy. And people who watched the game, they felt that it wasn't quite the real thing. So for TI, for a public match in late August, we switched to a single courier. Now here's here's an interesting fact. We've only had 5 days of training with a single courier before the biggest public matches. And despite that, it did very sensible things. But probably with a few more weeks of training, with a larger model, it will do a lot better still. So our remaining task is to decisively beat the best teams many times. But the real conclusion here is that actually, if you want to solve a hard problem with reinforcement learning, you just can. It's just going to work, just like supervised learning. It's the same story exactly. It was kind of hard to believe that supervised learning can do all those things. It's not just vision, it's everything. And the same thing seems to hold true with reinforcement learning, provided you have a lot of experience. You need a lot of experience. That's an issue. It needs to be fixed. But that's the situation right now. Okay, so this concludes the first sub-part of the talk. Now I want to switch to another result from OpenAI that I'm really proud of, and that's our robotics result. So one of the issues of training agents in simulation with huge amounts of experience is that you can say, well, but that can never possibly do useful things outside of that simulation. Well, here we addressed it a little bit. The goal of this project was to get this robot hand to reorient this block. And the way we did it is by training it in simulation in a clever way such that it will transfer to the real world. Now it's important to emphasize that our simulation is imperfect. We don't model friction very well. We don't model a lot of things. There are many things about the physical hand which we don't know how to measure. I will describe to you once the point of this part of the talk is to tell you about a very simple idea that seems to work. One other nice thing about our approach is that we were able to apply to multiple objects. We were also able to rotate this octagonal prism and not just the block. The core idea that made it work is called domain randomization. It's not a new idea. People were working on this idea for a long time. What we've shown is that this idea works really, really well. The idea of domain randomization is this. If there is something in your simulation which you can't measure, you randomize it, and you require your policy to be able to solve it for any value of the randomization. So what do I mean by that? Let's say that we don't know what the friction should be, because we just don't have a good way of measuring that. What we will do is that we will say that our policy needs to solve the problem regardless of the value of the randomization. I'm going to put it in a simulated world, and the policy doesn't know what the friction is. It needs to interact with the world to quickly figure it out and deal with it. So that's domain randomization. It's that simple. We also did it for perception as well. So here we have, these are examples of the images that the camera, the synthetic images that the camera has seen, which takes, you see the robot hand has different colors and different backgrounds and lightings and all that. And if you can deal with all that, then you can probably deal with the real world. That's it. That's the idea of the domain randomization. It's not a new idea. The thing that's interesting is that it worked. And especially that it worked with the physics. And we randomized some tens of numbers of variables. And I want to show you a nice graphics of how it looked like. Oh yeah. There was something really cool that we did. And that is, we were able, I want to tell you about the way we trained the perception module. So we designed the system in such a way that we have a controller which takes as inputs the coordinates. So it doesn't get to see the image. Now there is an advantage to training your simulated policy without vision, is that you don't need to render images, so you can get a lot more experience and train much better. So how do you include vision? So we trained a separate neural network which takes images and produces a prediction. And then we required that policy which was trained with the true state, with the correct state, also sometimes use the prediction by the convolutional, by the perception module. So instead of using the truth state, it would sometimes use that, and it was able to learn to adapt to this kind of inputs very easily. So the point is we were able to factorize the training of the control and perception, and that allowed us to save a lot of compute. And then when it's done, you just give it the real images, and you give it the real state estimation of the fingertip locations. You feed it to the LSTM and you get the actions, and the whole thing works. And fixing all the bugs here was challenging as well. Things like latency mattered a lot, the speed of the computer that runs the LSTM policy. We were surprised to observe a speed up when we changed the computer which would run the policy to a slightly faster computer, so then the neural net ran faster. The latency was reduced. But the idea is simple: domain randomization. If your simulation is different from the real world, you just randomize the thing you don't know, and you require that your policy deals with all these values. And this idea goes surprisingly far. It's not a new idea. It just turns out that it's a good idea. So the way we've trained both the DOTABot and the controller which manipulated the block was done using RAPID, our reinforcement learning infrastructure. And it actually, there is lots of shared code between the DOTABot and the robot training and the code which trained the manipulation policy in Dactyl. Now, there are obviously some differences as well, but it turns out that because it's so hard to write good scalable reinforcement learning code, it's worth reusing it. So that was nice. Oh yeah, I got another cool picture which shows you the 3 different cameras that look at the location of the block. So you got these 3 cameras, they look at the block, and that's how they estimate its location. Got a few more images of the vision architecture, which just takes the 3 cameras, runs them through a neural net, and outputs the positions, and the control policy, which is basically an LSTM. It's pretty amazing how simple all these architectures are. If you want to use vision, you just do a convnet, and it's always going to work. So this concludes the part about our dexterous manipulation results. Now I want to switch to talking about our language understanding result with unsupervised learning. And I want to tell you the fundamental thing about this result, which is all you do is you train a very good language model, and then you fine-tune it to language tasks, to language understanding tasks, and you get a big improvement, a very big improvement over state-of-the-art in many cases. That's it. It's the original idea of pre-training and fine-tuning actually working. The trick was to have a sufficiently good language model. That's quite nice. I want to give you a sense of the improvements, so you can see that on so these are a bunch of different tasks. The left column shows the before, and the right column shows the after. And the number on the right is almost always larger, and sometimes by a large margin. And you may not be able to see it all, but these, so let me show, so these 3 rows show you the 3 tasks where the improvement from our model was the largest. And these are tasks that require multi-sentence reasoning and understanding. I'm going to go over this example, just give you an idea of what is required. So the example says, Karen was assigned a roommate her first year of college. Her roommate asked her to go to a nearby city for a concert. Karen agreed happily. The show was absolutely exhilarating. And then 1, Karen became good friends with her roommate. Karen hated her roommate, which is more likely. It's that kind of thing. And just training a very good language model, fine-tuning it on this task, big improvement over state-of-the-art. And there's every reason to believe that if we train even bigger and better language models, the gap will increase even further. And I'll tell you a little bit about the details. The model was a transformer. I won't elaborate on the details of that, but I will say that I think it's one of the most important innovations in neural net architectures in the past few years. The data set is a large corpus of books. The size of the context is 512. So in other words, the language model gets to look at the previous 500 words, which is a nice context. And it's been trained on 8 P100s for 1 month. And I want to show you a little bit about how the transformer was used. So you got this transformer which takes so this is a diagram of the transformer. There are some details, but you can ignore it. It's like details. So this part is the transformer details. But if you're curious, I recommend you look up the paper. Attention is all you need. And then here we describe how we simply represent the different problems and feed them to the transformer. We do a bunch of sensible things. For example, if you have a multiple choice question, you feed the context and the possible answer to the transformer, you feed the concatenations, you get your 3 representations, and then you pass them through a linear model. And that's it. So really simple stuff. It's just that if you have a really good language model, you can solve language understanding tasks. And if your language model is better, your language understanding will be better as well. So that's nice. It looks like unsupervised learning is starting to show signs of life. It's an encouraging result. Next, I want to switch to the following, to the last part of the presentation, which is look at the trend that we have right now and try to understand if the current AI boom can reach all the way to AGI or not, and what's the probability of that. And the goal of this part of the talk is really to make the case that it's hard to lower bound the place we'll be in, let's say, 5 to 10 years. It's very hard to lower bound that. We may get the probability of an AGI, of getting to AGI, can no longer be discounted. And here, I want to talk about big technological revolutions that's already happened in the past. So there is a book called Profiles of the Future by Arthur C. Clarke, which is a really good book because it analyzes many of these technological revolutions, and it has lots of cool factoids there. And one of the things that it concludes is that with every big technological revolution, such as the airplane, spaceflight, and nuclear power, you had very vocal and very eminent detractors, people that felt that it's definitely impossible. And for example, with the airplane, various people said that it cannot be done, and then when it was done, the same people said that, well, sure, you can do it for one person, but it will never be economically viable. With spaceflight, an interesting thing that happened there is a mistake which Arthur C. Clarke calls failure of nerve, where the US analyzed the question of sending objects to space and concluded that it's impossible because you need to build a 200-ton rocket. So the Russians went on and built the 200-ton rocket. And in fact, the Astronomer Royal of the UK said that space travel is utter bilge 1 year before the Sputnik went into space. So that's pretty interesting. Next, I want to go and talk about the history of AI. When we looked at the history of AI, we discovered that our old understanding of the history of AI was not accurate. So what is the old understanding of the history of AI? is that the field went through a sequence of excitements and pessimisms about different technologies. So it was excited about symbolic systems and perceptrons, then expert systems, then backpropagation, then support vector machines. Now we're excited about neural networks again, and then in the future we'll be excited about something else again. But the reality is a little different in the following way. So when Rosenblatt presented the perceptron, he was really excited about it, and he made the following statements. He said, so that was in 1959, and it's very interesting what these statements are. So specifically, he said that it's an embryo of an electronic computer that will be able to walk, talk, see, write, reproduce itself, and be conscious of its existence. Later perceptrons will be able to recognize people and call out their names and instantly translate speech in one language to speech and writing in another language. It was predicted. So that was 1959. So Rosenblatt became really popular with the popular press, and he got all the funding. So then Minsky and Poppert got really upset. So Poppert admits that they wanted to stop, they felt that this direction was unpromising, and they wanted to stop progress in this field. They admitted there was hostility in their book when they wrote The Perceptron, and they felt that the claims that Rosenblatt was making were misleading, and they were taking the funding away. And Minsky directly admits that he was concerned that other areas of AI were not getting funding. And they wanted to make a case that in their book, progress in neural networks is impossible. And then in the 80s, computers became cheaper, and the cheaper computer has increased interest in artificial intelligence, in neural networks. And then in this context, the backpropagation algorithm was invented. And there is a funny quote from Minsky and Poppert about the backpropagation algorithm. We have the impression that many people in the connectionist community do not understand that backpropagation is merely a particular way to compute the gradient, and have assumed that backpropagation is a new learning scheme that somehow gets around the basic limitations of hill climbing. Another very interesting thing that happened is that, so let's see, so where does it lead us? So then the alternative interpretation is that neural nets research and the wave of neural nets that we see right now is not a 5-year wave, it's a 60-year wave, starting with the perceptron. And as compute was getting better, the results became more impressive. In the early 90s, we already had TD Gammon, which was a self-play reinforcement learning system which was able to beat the best humans in backgammon. And one interesting fact about TD Gammon, by the way, is that the total compute that was required to produce TD Gammon is equivalent to 5 seconds of a Volta. So now that we have the alternative, the other interpretation of the history of AI, in other words, that neural nets have been the one persistent thread in the history of the field, which has been growing and getting better as compute has been increasing. Now I want to survey a sequence of results over the past 5 years, and to see how they changed our beliefs as to what's possible and what's not possible. So with the original AlexNet results, before that result, it wasn't really believed that neural nets can do anything, and obviously they can't do vision, and it would be totally crazy that neural nets could solve hard problems. And by the way, one cool thing is the image here, which I got from Antonio Torralba, which shows the performance of vision systems before neural networks. So do you see this little red rectangle? So it thinks that it's a car, because here it is zoomed in, and here's how it looks like once you apply the Hog vision transform, the Hog feature transform. So it didn't work, and it wasn't going to work. And then it turns out that a large convolutional neural network with supervised learning can do pretty well in vision. Then with DQN, okay, fine, so maybe you can do vision, but it then turned out that you can take neural nets and turn them into agents that learn to achieve goals. And what that did is that it gave everyone, researchers, the idea that it makes sense, and it's a sensible, it's a sensible question it's a sensible research direction to give neural networks the goal, to use neural networks to build agents that achieve goals. Now, after vision came neural machine translation, and the belief was, sure, you can do perception, but you can't do things like translation. I mean, come on. That requires tens of thousands of lines of complicated code and various state machine algorithms and graph algorithms. But turns out that no, if you just use a big neural net correctly, you can just do it. Then AlphaGo arrived. And before AlphaGo, the kind of belief you had about reinforcement learning is that it's actually not good for anything. It only solves tiny toy problems. But now, with AlphaGo, it turns out that reinforcement learning in the form of Monte Carlo tree search can solve a very difficult task. A truly difficult task. After this, we have OpenAI 5. Well, fine, sure, you can solve something like Computer Go because you have a small action space. The game is discrete. It's nothing like the real world. Surely you can't solve a game like Dota or StarCraft, which is continuous and messy and more similar to the real world. But it turns out that if you just scale up reinforcement learning, you can do it no problem. Okay, so fine. So maybe we can do things in simulation. But you definitely can't take things outside of the simulation because you need so much experience inside the simulation. How can you possibly use these algorithms outside? But it turns out that if you change the simulation a little bit, you can in fact transfer skills from inside the simulation to outside, as we've shown in our work on the Dactyl robot. Okay, so then you can say, well, fine. So maybe you can achieve goals whenever you have a cost function that clearly describes what you want to do. So in supervised learning, you want to minimize your training error. In reinforcement learning, you want to maximize the reward. But you can't possibly do unsupervised learning. That would be too much. But it turns out that you can do unsupervised learning as well. If you simply train a very large neural network to predict the next beat of your signal. And so far, we've shown it for language. It needs to be shown for other domains as well. Finally, I want to talk about the underlying trend that was powering it all, and that's the compute trend. So it is pretty remarkable that the amount of compute from the original AlexNet result to AlphaGo 0 is 300,000x, and you're talking about a 5-year gap. Those are big increases. It's a 3.5 months doubling time. And I want to show you a visualization of the scale. So this shows all the different results, and we are basically zooming out with the scale. So you see let's see. Yeah, it took a while. We've included some of the early results from the 80s, so that's why it took a while to get to the point where, the dropout net and the AlexNet are even shown. You can see the end. But it keeps going. Then you have the SIG-to-SIG compute is becoming small. The VGG compute is becoming small. But it keeps going. So that gives you a sense of the increase in compute that occurred over the past 5 years. And finally, we get to a point where even AlphaGo 0 starts being visible. Yeah. Now, a lot of it is being powered by data center computing. In other words, there are limits to the amount of compute you can put on a single chip, but then you just get many chips together. And that's going to be more important moving forward. And I think that one thing that will probably happen is that just like with the very large rocket that the Russians built in order to go to space, it will be important to have very large clusters in order to get to the truly large amounts of compute. But it's probably going to happen. So, to conclude, the point of this part of the talk was to show that while highly uncertain, it's not possible to determine a lower bound to progress in the near term, and maybe the current wave of progress will actually lead us to AGI. And what it means is that it's worth proactively thinking about the risks, about addressing questions like machines pursuing misspecified goals, machines subverted by, deployed systems subverted by humans, and just general, very rapid change, out of control economy. These are good questions to think about. And that's all I have to say. Thank you very much.
Thank you, Ilya. We have time for some questions and answers now. There are microphones at both sides of the room, so the people on YouTube and at remote sites can hear. Please go to the microphone if you have a question.
You said supervised learning can solve any problem. How about hard mathematical problems, like prime number detection, by labels on random factors?
Yeah, I mean, the precise statement is that supervised learning can solve any problem that a human can solve in a fairly small number of seconds.
Hi, I'd like to ask a question about your thoughts on safe reinforcement learning and what directions of safe reinforcement learning dealing with huge imbalances in data sets when you have high importance examples. What directions do you think are interesting and worth pursuing?
So you asked about safe reinforcement learning and data imbalance. So I mean, I think when it comes to, so let me answer the easier question first. Data imbalance, there are lots of standard tools, there's lots of approaches you could do which are pretty standard. You could train a small model that will try to recognize the important examples which you then would feed to the large model. You could do things like this, and this is already been done. In terms of safe reinforcement learning, I think that like the kind of work that we do is, for example, learning reward functions and preferences from human feedback. That is one example of an area which we've pursued. And other good areas include basically safe exploration would be another one, where you try to limit the change to the environment as you explore. This would be another example.
Over there.
Very nice talk, thank you. So I'm curious, you mentioned some of the criticisms of deep learning over the years, and I'm wondering, so sample complexity, I guess, is one big issue. I'm curious, a critic today might say it's horrendously sample inefficient. What are some things that you see, and is that even an issue? Or what are some things that you think might address that? Thank you.
So I think sample complexity is an important issue which has to be addressed. There's no question about it. And some of the more promising ideas right now look like transfer learning and training your system on other tasks. So for example, with the language results which I presented, you train a big neural net to predict the next word in a very large text corpus. And by doing that, you greatly reduce the sample complexity of this model for other language tasks. So this is an example of how you might go about doing that. Yeah.
An argument that a critic could make is that the problems where you've shown the best results so far are problems where there is high signal to noise. Do you have any thoughts on other areas where you have worse signal to noise?
Can you have an example?
Medicine.
Medicine. Yeah, so in order to move to environments like this, several things will need to happen. We'll need to get really good at unsupervised learning, and we will need to get really good at inventing or discovering reward functions for ourselves, which you could then optimize. So in other words, once the agent can choose a sensible looking reward function for itself and then optimize that, it will both gain skill and gain new data for its unsupervised understanding.
Thanks for the talk. One thing you mentioned was that in vision, people seem to have really converged on deep convnets as kind of the one architecture that can solve basically all the problems that you run into. We haven't really seen that with sequence models. You guys use LSTMs in some places, transformers in other places. There are also the sequence convolution models. Do you think there's going to be a similar convergence for sequence models, or are we going to continue to have kind of a zoo of different things, and what's going to work best is going to depend on the application?
I mean, it's hard to predict that. I think it's definitely possible that there may be... I mean, it feels so... I think it's very possible that there will be several alternative architectures for sequences. I mean, to be fair, even for images, you have new candidate architectures like the image transformer, which may potentially become a more dominant architecture than the convolutional, than the conventional convolution. So I think in some sense, yeah, I mean, there is a chance we will have some, let's say, 2 or 3 alternatives. But on the other hand, it's only 3 alternatives, it's not so many.
Thanks.
Hi. In the case of the deep Q learning, I remember there was a result from several years ago that they couldn't solve the roulette problem, right? Because if it has no understanding that the roulette wheel has to be balanced, just from the samples, you're always going to think that some piece is like lucky for a period of time. So I'm just curious, just in general, do you think that that's not really like an issue anymore in terms of with enough samples you can learn the rules of the universe, or do you have to still code some of those in for cases where the rewards are like really, almost designed to be, to have high enough a variance where it's difficult to learn it, just by averaging the outcomes?
Yeah, so I can talk about the, your broader question. I didn't really understand what you meant by the roulette problem.
Okay, I can explain it very quickly. So this was the example for the double Q learning network. And their point was that they actually proved in that paper that with regular Q learning, you're basically it's the outliers are such that if you don't know the properties of the roulette wheel, that every single point has to be the same and random. If you just treat them, if you treat the roles of the roulette wheel as independent variables, then no matter for how long you run, it's just never going to come up with the answer that all the numbers are negative. There's always a long enough row. Sorry, I'm explaining this poorly, but
So I mean, so it sounds like, and the question is. But then the question is something broader. The question was, and therefore, sparse rewards? I didn't quite understand the question.
Yeah, well, I'm saying you solve that problem very easily by just sort of specifying that all the points have to sort of have the same underlying probability. But without coding that in, if you just look at them independently, just from you can have an infinite number of samples, and you never really learn that all the numbers are negative.
Yeah, so you definitely want to, in the long term. In the long run, you want to be in a place where you don't hard code, because the set of problems you want to solve is so vast that I don't see how humans would be able to hard code useful things. If you have been able to hard code something useful like the convolution or the recurrent net, that's pretty useful. It's also very general. Like, you do want to hard code very general assumptions. You want your models to make use of all available information. The way you will probably deal with very, situations where you don't know what's going on is by benefiting from other sources of information. That's what people do. When we approach a new problem, we don't start from scratch. We have all our life experience, and when things look confusing, we try to go to Google and talk to someone else. And that will be, at a high level, the way we will deal with totally new domains. But I think that it is definitely desirable not to hard code things because it makes life easier. And it just seems unlikely to me that we will be smart enough to be able to hard code things for the truly difficult problems. So I'm also, broadly speaking, bearish on this approach.
Yeah, no, I completely agree. That's just a funny example with games. These things are independent, but it's hard for the algorithm to learn that. In real life, you actually don't know, right?
Yeah, so I'll need to look in this example in detail to form a definite opinion.
Hello, thank you for the talk. What's the next hardest game in your opinion? Is there anything that reinforcement learning can't learn?
I mean, There's definitely things that reinforcement learning can learn. I mean, one of the downsides of the way we've learned Dota is that we needed millennia of experience. So while we can learn, while you can learn very hard problems if you're willing to gather sufficient experience, how do you do that with less experience? So I think that is a better description of the challenges that are coming next. In terms of solving hard games, I mean, I don't think that if you don't restrict the amount of experience you get, I don't think that there are games that are really worth solving.
Hi. So RLs have been used in NLP, but not with that much success, like in abstractive summarization and things like that. So what is your general view about that, and what, according to you, is a good task in NLP where RLs can be used?
Sorry, what has not been used in RL?
In
NLP?
natural language processing, I'm saying that reinforcement learning.
see.
Yeah.
Yeah.
So what, according to you, is like, why is that the case, and what would be a good task in NLP for RL, to be solved by RL?
Yeah, I mean, I think that makes sense. With RL requires that you can figure out the reward function and that you have an environment. And in NLP, you don't have both. So I think things like, let's say, like assistants, like dialogue systems, they can benefit from RL. Or for example, you know, have you seen the Google Duplex? Mm-hmm. Like that's the kind of thing where you can say, hey, like, yeah, you have 10,000 people talking to your system, and you know, if the system makes a mistake or doesn't do what it's required, they press a button to give it a negative reward. That would be an example.
Okay, so you're positive about using RL and NLP?
I mean, for sure. I just think it will look a little different from the current applications. And in particular, I don't think that, so NLP is mostly data set driven. So where is the RL? So you need to move away from the data set. You need to have an environment. So you either have agents talking to each other, but then they won't talk real language, or you have agents talking to humans. But then it's just logistically difficult, and only there aren't that many research labs that could do it.
Okay, thank you.
Okay, if there are no more questions, let's thank Ilya again for his talk. And I'd like to give him a little something to thank him for taking his valuable time and sharing his thoughts with us.
Oh, thank you very much.
You're welcome.
Cool.